All right, something to be aware of is that you can write the Redington conditions in terms of modified uh, duration and what's called modified convexity, and this is pretty trivial stuff here. Um, second, yeah, so what's going on here is as follows. So I'll just write down the first Redington conditions. One, well, the first, I'll write down the three Redington conditions. So in particular, just um, at t equals 0, the present value, this is the first one. So the second one is p of prime. So I could do something trivial here, given 1. What I could do is divide both sides. Well, I could take a minus both sides. I'll do this. I'll do it this in red. Doesn't matter what I do it. I'll do it in blue, I guess. So let's do minus both sides. Let me divide by, doesn't matter. Let's say present value of my assets. But the present value of assets is the present value of liabilities at my given interest rate. That's exactly what 1 is. So this is really nothing more than present value of my liability. And so I'll do this in red now. Remember, this is modified duration. So 2 is exactly the same thing as saying modified duration of my assets is equal to the modified duration of my liabilities. So I think what's important to remember is that it's just exactly the same. It's your and I'll explain what I mean, why it's important in a second. So let's do the third condition. I'm going to do basically the same thing. So we need the second derivative of assets to be bigger than the second derivative of liabilities. Now I'm going to divide again by the same thing. I'll even do it in blue again. But I'm justified here from 1. Again, these two are the same. And this is what we call modified convexity. Convexity is like a fancy word for two derivatives. If you take data science and machine learning, you might take an optimization course where we talk a lot about convexity. So this is modified convexity of my assets. And it's really definition. By definition, this is modified convexity. We define rather modified convexity to be this, and we define this to be modified convexity for my life. Okay, right. So yeah, that's why this is true. What's a lot more interesting, well, at least this part, 1 and 2 is not interesting because what I could do here is just simply, I don't have room, but I can just, oh yeah, plenty of room. Multiply by, so here I can just do something kind of dumb and multiply by 1 plus I to get Macaulay duration. Or 1 plus I. Right. So now all of a sudden this is MACD. So Redington conditions, at least the first two, can be written as matching liability, matching the present value of liability and assets, and matching their Macaulay durations. Right. Now, in terms of has convexity, let's get rid of this. Um, There's something called Macaulay convexity, which, as we'll see later, is actually really, really, really useful and interesting. Even Macaulay duration, that we're allowed to match Macaulay duration, that's actually extremely useful, as we'll see in a minute. But yeah, you can show actually that all three of these is equivalent to all three of these. Again, I'll explain why that's useful in a little bit. And if you want to actually see the derivation, it's right here. It's not that bad, but it is a little bit much. But anyway, so kind of comparing um, modified convexity and Macaulay convexity. These two are bigger than each other precisely when these two are bigger than each other. Yeah, if you're curious about it, let me know. All right, so just some examples. 104. I'm not going to do this one, um, but yeah, they're saying you match duration, and you match the present value um, of the obligation. So it's the present value of the assets is matching the present value of the obligation, and you're matching duration. It doesn't tell you which duration you're matching, but it absolutely does not matter. And I think the punchline here is that you would do this, despite all this, you would do this problem exactly like you would do the previous problem, this one. So I won't do it, but you would do this problem exactly, or you do this problem rather exactly like you would do this. And in particular, the first time you have um, you have a liability or an asset. Well, actually, here it's actually nice because the first time you have a liability or an asset is exactly X. Sorry, is exactly today. So that's T equals 0. So automatically you would basically do this here because you'd do this, but T0 is 0. So it's exactly doing this. So yeah, if you want this, you want to see this done. This is 104. You could just go to 104, and yeah, they're going to do exactly what we did, just that T equals 0. Right. So really, they're just even that they're not really matching duration. They're just literally matching second derivatives and first derivatives. Oh, sorry, they're matching the present values and the So actually, they're doing something kind of weird. They're doing like they're actually defining one function as the present value of assets minus the present value of liabilities, and then setting that to be 0, setting the derivative to be 0. It's the same thing we're doing essentially, but it's kind of weird that they do that for one of these problems or some of these problems and at least one of these problems, and they don't do it for other ones. Yeah, the solutions here can get really weird. I'm not sure why. You want to see this done? Let me. Um, yeah, so here's another example. This is really, really, really easy. I don't think I'll get this easy of a problem. But here's a table of modified duration and convexity. They don't tell you which convexity. It doesn't really. I mean, I guess it's definitely going to be modified convexity because if it was Macaulay convexity, you wouldn't know what to do. So it's really all three of these are true is the same thing as all three of these are true. So you have to do everything with respect to, or particularly two and three together. One, two, and three here is equivalent to one, two, and three here. You can't just mix and match. So yeah, here the answer is literally nothing to do. The answer is clearly uh, sure. The answer is clearly B because for company U, you have present values matching. You don't have duration matching. You don't have modified duration matching. So that's out of the question. Here you have present values matching, you have modified duration matching, but the convexity for the assets is smaller than the convexity for liabilities. Here you have present values are equal, assets are equal, sorry, the modified duration is equal, and the convexity is bigger for assets than liabilities. So the modified convexity is bigger for assets than for the modified convexity. Okay, so what I want to do next, and this is just something to keep in the back of your head. I admittedly don't see this too often on Exam FM, but yeah, it's easy enough to keep in the back of your head. So I want to put this to very good use. And this is, if you think about it, what I have here is quite special. In particular, I have a very nice formula for basically the third part of Redington condition being true if I'm given the price of my assets at t equals 0. In particular, this here is exactly the price of my assets at t equals 0 at whatever interest rate we're looking at. Right? So that's extremely useful at times. Okay. So let me just kind of go over what I just said. So remember that, well, first, the price of the present value of my assets is just present value of, well, add up the present value of your assets. Not much to that. You're discounting your assets appropriately. Okay. So remember the formula for Macaulay duration is you take P prime over P times 1 plus I. So what does that do? Well, you divide by the price, which, as I said before, is the total price, but multiply by 1 plus I and take minus. I forgot the minus. That gets rid of this pesky term here. So you basically get rid of this here. You just have this over the total price. And this is extremely useful if you're given the price of your assets. Right? And implicitly is that this is the price of the assets at your given or at whatever interest rate I we're looking at. Ultimately, we're going to plug in the given interest rate. So these are going to be the prices of your assets at the given interest rate. And yeah, same thing here. Remember, I said Macaulay convexity, the formula is right here, but each AT 1 plus I minus T is the price of your asset at T. So, and sorry, it should be T equals 1 to N. It doesn't matter because when T equals 0, you get 0. So T equals 1, T equals 0, it doesn't matter which you start off with. Right. So this just, yeah, gives us a very convenient way uh, to basically figure out whether the Redington conditions are true or not. Right. So let me do an example. Okay, what I want to do next is put this to good use. Sorry about that. So I want to do 108, and I'll actually go to the website here. So you're given the following information about a company's liabilities. You create a portfolio by making one of three investments: a 5-year, 15-year, or 20-year zero coupon bond. So very simply, that just means you have assets that, well, you buy assets that give you money at 5 year, after 5 years, 15 years, and 20 years. So you want to do Redington immunization. The yield rate for everything is 7.5. I guess they technically don't tell you what the yield rate is for liabilities, but you're not given any other piece of information, so you have to assume it is 7.5. Figure out what portfolio you get. So, yeah, and so here you don't need to know what the price of each liability is. You have no idea what these liabilities are. You have all the information you need for the liabilities to set up the equations, or the 1 through 3 for Redington immunization given Macaulay duration and convexity. But you have all these different options for the price of these different assets. And so this is perfect cannon fodder for what we just had a minute ago, right? So, right. Let me do something real quick. All right, so, yeah, this is not too bad of a problem. So let's say X, Y, and Z, whatever you want to call them, it's fine. Let's say this is the price of 5-year zero coupon bond. This price of the 15-year bond, and this is the price of the 20-year bond. Okay, so one thing to be clear, and you want to understand this. So this asset occurs at the zero coupon bond. You invest money now and you get stuff after 5 years. So this occurs at t equals 5, t equals 15, and t equals 20. So let's go back here. So, so first, let me just do something kind of obvious here before I do anything else. Black. Okay, so I want to set this up. So 1 is kind of, there's really not much to 1. The total price, actually, let me, right, quick. So the present value, the total, which is the price of the liabilities, is 9,697. So 1 is simply, well, total price of your assets is X plus Y plus Z. When I say price, I mean present value at t equals 0. So that's 9,697. 2, we're given a Macaulay duration of liabilities is 15.24. So what's the Macaulay duration of my assets? Well, here we're going to use this right. Here we're going to use this formula here that we had before. So the only t that we have an asset is at 5, 10, and 5, 15, and 20. So we're going to divide by the total price, X plus Y plus Z. And then we're going to stick a t. Well, it's going to be 5x because that's when the x occurs at t equals 5. That's my asset at 5. Anything before that is 0. Anything between 5 and 15 is 0. So the next one is 15y, and the last one is 20z. Again, that's the only t's that we actually have an asset at. So this formula says it's the price of the asset at t, but stick a t here. Okay. Stick a t in front of it. So the numerator is 5x, and this is going to look like a nightmare, but it's not super bad. Explain in a second. Move this over a wee bit. Whole thing over x plus y plus z. Right. 3 is going to be almost the same thing. I mean, it is the same thing, except instead of a t, it's t squared. And we're given the Macaulay convexity of the liability is 24246. So we have here, as well as move this down a tiny bit, is 24247. That is going to be not equal. It's going to be bigger, less than 5 squared x plus 15 squared y plus 20 squared z all over the total price, x plus y plus z. Okay, so this is an absolute mess without looking at the problem. Not even the problem. We have all that we've utilized all the information in the problem. So to be absolutely clear, using this little trick, given the prices of my assets, we don't need the prices of liabilities. We already are given the total price, Macaulay duration, and Macaulay convexity of the liabilities. But given that little trick formula, particularly for assets, we have written down 1 through 3 for the Redington conditions. And implicitly, this is at this given yield rate, 7.5%. You don't really need to use it. And I would say more to the point is, I'm not even sure if you can do this problem using it. Maybe you can in some weird, funky, inefficient way, but yeah, I don't even see how to use it. So it's really just superfluous information to try and get you influenced. Okay, anyway, so what do we have to do next? So this would be damn near impossible if they just said solve for X, Y, and Z. They're not. They're giving you options. And particularly if you think about it, there are 2 possible situations. One is y equals 0. That's so you can just plug in and get and check. Not very efficient, but you can do that. You literally plug in all of these and check which one is going to be correct. Maybe a more efficient way to do this, which actually the PDF does, PDF solution, if you go to it, you should notice that there's 2 options. Either Z is never 0. Y either equals 0, which is the first 2, A, B, or X equals 0, which is the last 3, C, D, and E. So I would look at those 2 options and then go from there. Like I said, this is honestly what the book does, the SOA solutions do. I actually used to just guess, but this is definitely more efficient looking at these 2 cases. So yeah, I'm definitely I'm glad they do it because I would not have thought to necessarily do it this way. Um, so let's do y equals 0. So in particular, if y is so if here if this is 0, that means, well, obviously, z, you can solve for x. X equals 9, 6, 9, 7 minus yeah, sorry, z. Right. So I can plug this in. So that's all one tells us. Now we can do 2. Um, yeah, I would just plop in. So it's 5x plus 0. I'm not going to write the 0 plus 20 9, 6, 9, 7 sorry, I'm going to plug in. Yeah, I'm going to plug in for z. Apologies. That would be left alone. So it's 5 times 9, 6, 9, 7 minus z plus 20z over 9, 6, 9, 7 minus z. Well, so you don't have to plug in. So let's be a little smart here. What's the denominator? X plus Y plus Z. X plus Y plus Z is just 96, 97. So this is just dividing by 96, 97. Again, just X, Y, Z is 96, 97. So why not just plop it in? And this equals 15.24. This is really easy to solve for Z. I'll let you do it. Z is 66, 1982. I guess I'll just get it real quick, show you how I would do it. So I would multiply 9697 times 15.24. Get that. Then subtract 5 times 9697. And then we have 15z in the numerator. So 661982. I think I'll need it, but I might. If anything, it's just worth it to store in the calculator, I guess. All right, so right, so now we have z equals this, and x is 962 minus z, and what is that? 30728. All right, so do we have this anywhere? We do. So I'm not sure why this is a little bit off. That's why 9697. I don't know why I did 96. So just add 5. Yeah. Strange. Sorry about that. Yeah, so we get that 3077 and 6620, but we gotta check if 3 is true. And I would just plop in. It's as simple as that. So store this in the 2 spot. So remember that Z is the first spot and X is in the second spot. All right, so yeah, let's just check. Those, to me, this would be the kind of problem to maybe get everything else that you're confident in and then do this, because there's just no substitute. One thing, there's no substitute for time in this problem. And I want to be clear about immunization problems. We'll do one more type of immunization problem. These are easy, but they're time consuming, and there's just no way around it. So yeah, I would say these are the kind of problems. Do some of the quicker ones first, and then go back to these as ones that you know you can do. These take a few minutes to do. So anyway, so 5 squared times x plus 20 squared is 400 times z over, well, we know x plus y plus z is 9697. So that is 281. Is that the solution? Uh, uh, sorry. Oh, wait. Okay, the solution is A. Some reason I didn't think, I thought it was not A. But yeah, as we got 281, well, that exactly 281. So interesting. That exceeds Macaulay convexity. Um, but yeah, so I'm not going to do it because, well, you do the first case, you get the correct answer. Only one of these can be right. We did check that the Macaulay convexity for assets is 281, which is bigger than 242.47. Macaulay convexity for liabilities. But yeah, if it didn't, if it wasn't the case that yeah, what we just computed is bigger than 242.72.47, then you would just do the second case, which is, I'll start it off. That is x equals 0. Right. And so when x equals 0, I'll just do this, and then not going to go through everything, but it's kind of the same thing. So yeah, it's weird. It's almost like I feel like you just found a $5 bill on the street that do the first case to get it right. Um, yeah, so if this equals 0, this, so that means right, y is 9697 minus z. And so yeah, you would basically do the same thing, except it would be 15 here. I guess they can just do it. It'd be 15 here because it's x is 0, it's 15y. Well, I'm not going to do it, but then you would get well, you can do this. Yeah. What would you get? They do the actually other two cases. You can get y is, yeah, so yeah, you can check that this is true. Knowing that this is still there. Well, okay, that's really irritating. So yeah, setting X gives you 9, 20, 31, 54, 465, 46. That is here. That is E. So if you're wondering, well, does that mean E is correct? No, because you compute the convexity, you get 233, 40. And that is smaller than 242, 47. And it's not good. We need it bigger. All right, so long. Take care. One more video. We're done.